Hello, in this video I'll try to explain the assembly language program to add 10 numbers pertaining to embedded controller lab, and also I'll explain the how to use Keel microvision tool to execute the programs related to embedded controller lab. Let us look into the usage of tool. Okay, uh, you click on an icon with the name Keel microvision 4. So we are using Keel tool to develop and execute the program in embedded controller lab, and after opening that you click on project and close the project. So if any current project is open, that will be going to close, and again you click on project, select new microvision project and give the project name. Now I'll give the name of the project as 10 number the addition of 10 numbers. I'll give the project name as 10 number. Any project name can be, any name can be given as project name, and save it out. And then you have to select the device. It asks for the device. In our laboratory we are going to use LPC1768 microcontroller as a device. So that belongs to a company called NXP. Okay, that's founded by Philips. So you have to go for an NXP company. Okay, and you enlarge that and you'll get try to select a device LPC1768. Okay, so the device is LPC1768. You select it out. Right side the window, the description regarding that device will be displayed. You can refer that. Click on OK. Okay, yes, click on yes. Okay, a target file will be created. Under that there will be a source file. By default, startup file underscore lpc17xx.s will be added to this source group, and this .s extension file pertaining to assembly language. And in order to execute the C programs, you have to add a startup file with an extension .c. Okay, now to add the startup file pertaining to a C program, the procedure is you have to right click on source group. Then there is an option called add files to source group. You select that, and by default that startup file pertaining to C program is stored in the C drive. Okay, while installing the tool, by default that folder will be located in C drive. So you have to browse the C drive. Okay, in C drive the folder name called Keel. Within Keel folder there's another folder name called ARM. There you have to search for startup file. Then the device is from company NXP, and then you have to search for LPC17xx, and system underscore LPC17xx.c file has to be selected and add. Okay, and close this. So this is the procedure to add startup file pertaining to C program. Okay, now after this go to file, create new file. So this is an editorial window where you can develop your program. Right? So now I'm going to save. I already have a program. I'll explain the program later. First I'll going to copy paste the program. So this is a C program. Okay, so if it is a C program, you have to save that file with an extension .c. I'll save this file name as add 10 .c. Okay, add 10.c and save it. Fine. Similarly, if I'll go for new file. Okay, and I'll going to paste the assembly language program. Okay. If it is an assembly language program, you have to save that file with an extension .s. Okay, I'll going to add, that means I'll save this file as .s extension file. So I'll call this as 10.s. So this is how to write the program and save the program. So I'll repeat that. If it is a C program, you have to save that file with an extension .c, and if it is an assembly program, you have to save that file with the file name with an extension of .s. Okay, now I'll come to the program flow. Here in the C program, I had included an header file because lpc17xx.h, since we are using lpc1768 microcontroller, all the associated registers will come under the structure lpc17xx.header file. That's why this header file should be included. Now this is a statement to call to declare an external function, an external subroutine. The name of the subroutine is sum10, and it does not return anything to the main program. It's a void type of function or void type of subroutine, and especially this subroutine is written in assembly language. Okay, we are invoking a subroutine which is written in the assembly language in this main program. Now this is an initialization of the main program, where system initialization, it's a CMSAS function. This should be included to initialize the system pertaining to LPC1768. Now we are calling a function called sum10, and this sum10 function is actually written in assembly language. Okay, and once that function is executed, your control for program control will come back or return to the main program, and it will halt in the and it is going to halt at this stage. So this is about the C program. Now let us consider once when this C program calls sum10, your program control will go to an assembly function so that it's going to execute a piece of program. Let's look into the assembly program. Here area sum code read only, it is an assembler directive. So this directive is going to reserve a code memory or read only type of code memory with a name called sum. Okay, this is an assembler directive which gives an direction to the assembler. Similarly, the other assembler directive is export sum10. So this export is an assembler directive that gives reference to the linker. So the sum10 is a what function name which can even refer outside this environment. So in order to give the reference to the linker, the export assembler directive is used. Entry is also an assembler directive which indicates the entry point of the program, or the first instruction to be executed is indicated by this entry assembler directive. Now sum10 is a label, and which just indicates the or holds the address of the first instruction. It is an optional, but in this case, since this sum10 is referred as a subroutine, it is essential to write the label here. One more important thing is label should be written to the extreme end, and the instruction and the assembler directives should be written by at least one tab space. One tab space must be given to the assembler directives and the instruction, whereas labels should be comments at the from the first point or at the starting point of the editorial space. Okay, so that is the difference between label and the positional difference between the label and instructions. Okay, now the first instruction is move r1 #10. So in this is a data movement instruction where a decimal number 10 is copied or loaded to a register r1, say immediate addressing mode. And now, or after execution of this instruction, the register r1 is going to hold a decimal value 10. Similarly, to the another register r2, a value 0 is loaded. Now the loop is a label. So within this loop label, we have an instruction called add r2 r1. So this adds nothing but addition instruction. Here r2 r1, these r2 r1 is acting as an operands. That means the content of r2 will be added with r1, and the result is stored to r2 register itself. Here r2 is acting as both source and destination register. Okay, originally before addition this acting as an operand, and that means a source register, and after addition it is acting as a destination register. Now the subtraction instruction is used here to decrement the content of the register 1, since we have to add 10 consecutive numbers. Initially the value of r1 is 10. Now it is going to subtract by a value 1. So thereby after subtraction the register value 1 become 9. Now after execution of this statement, the r1 is equals to 9. Okay, now the next instruction is a branch instruction. BNE stands branch on not equal to the specified label. Here the specified label is loop. The branch on not equal and branch on equal instruction should be used in association with subtraction instruction. Okay, so after subtraction instruction, if the destination operand, if the destination register value is 0, this condition is going to false, and it breaks the loop. Okay, otherwise if the destination register is it does not equal to 0, if the destination register is have some value, then this statement returns with true value. That means it returns with true, and these two addition and subtraction statements will be executed further. Okay, so now in this case, after subtraction, r1 becomes 9, and since it is not equal, again the program flow or control flow is go back to an instruction called add. Okay, similarly it's going after this execution of this instruction, we are going to add previous value of the r2 is 10, and we are going to add with r1 now it is having 9, 10 plus 9, and that addition result will be going to store to r2. So thereby 10 consecutive numbers is going to add, and at the end of the 10th addition the result will be stored in r2. Once the r1 is decremented to 0, that means when 1 minus 1 leads to 0, this statement returns with false value, and the loop will not execute, and it's going to execute a statement called bxlr. bxlr stand branch termination. Since this is a subroutine called by a C program, so to return to the main program, this is a bxlr statement must be executed. Whenever it is a subroutine, to return to the main program, the bxl branch with link register should be executed. Now the link register is a register which holds a copy of the program control PC value, that is program control control value, so that it provides the address of the instruction to be executed next in the main program. And this end is an assembly directive, indicates the end of the program. Okay, after bxlr, your control flow go back to main program, where it has while one statement, your program will halt at this stage. Okay, so this is about the program flow of addition of 10 numbers. Clear? So after developing your program, then you have to add these files to the source group. Okay, you right click on source group, then add files to the source group. See, my file is C file is add10.c. you select the C file and add it. That file will appear in this list and close. Similarly, you right click, add files to source group, and here file type is selected as C, and if you select file type as ASM, so you're going to find another file name called 10. Okay, 10.s. select that file, add and close. Okay, so this whatever the file you are used to develop your program, along with the startup file, all those files must be added to the source group. Okay, after adding these files to the source group, you have to perform just building of the target. So right click, there is an option called as build target, or else there is a shortcut here, you can even click on that. Okay, now this build output window will pop up if any errors, syntax errors in your program. It doesn't show any logical errors. If any syntax mistake or syntax problem, that is going to display in the build output block. Okay, after erasing all, or after rectifying all the syntax errors, so it's supposed to show 0 errors and 0 warnings. Clear? Now if it is a part B programs, like interfacing programs, you have to download a file to the LPC1768 microcontroller. That file is an hex file. To create the hex file, there is an option called right click. Okay, right click on target, and there is an options for target 1. So there you have to select a target. Okay, in that select an output. There you have to check for create hex file. Okay, ensure that in the output tab the create hex file must be checked, so that after execution, so after building the target, it's going to create the hex file, and this hex file can be downloaded to the LPC1768 microcontroller. Clear? And also in a linker tab, you check use memory layout from target dialog. So these are the procedure you have to follow in order to create the hex file. Clear? Click on OK. Now you build or rebuild the target, and returns with it also creates an hex file. Okay, so the hex file will be created. So this is about how to develop a program with the help of Keel Microvision tool. This X file can be downloaded to LPC1768 microcontroller. This procedure has to be followed for even rest of the software programs, where all the software programs is written only in C language. So we have to add only one file with an extension called .c. Okay. Let us look into how to debug the program. Okay. So there is an option called debug, where you have to start stop debug session. Click on OK. Now in this window you can observe the registers, all the associated register of LPC1768 microcontroller architecture will be displayed here, and their initial values also displayed here. Okay. And there are different options are there. For example, if you press F5 or run command, the complete instructions will be executed in one stretch. Or else if you want to execute line by line statement, you can use a shortcut key F11. Now let us deal with line by line execution. Okay. Now initially the startup files will going to execute in .c. There is a system initialization function. That function is being executed. Okay. After these are all the system initialization functions. After execution of the system initialization, now it's going to execute another statement called sum10, where it's going to call a subroutine written in assembly language. So this yellow arrow indicates the instruction or the program statement to be executed next. Okay. After execution of this, your program control moves to a subroutine which is written in assembly language. These are all the assembler directives, so they are not instructions. Okay. Now the first instruction to be executed in assembly language is move r1 comma 10. Look at the register value. Initially the r1 has some value. Okay, there's some value. Now in this statement we are trying to load, or we are trying to move a decimal value 10 to the r1 register. Now I'll execute this. After execution of this instruction, look at the r1 value. Now the r1 value become 0a, that is in hexadecimal. So that means the r1 loaded with value 10. Now the next instruction to be executed is move r2 comma 0. Now before execution, the r2 register has some value, okay, some default value. Now after execution, the r2 register become 0. Okay. Now the next instruction to be executed is addition of r2 comma r1. The value of r2 is 0. The value of r1 is 10, that is a. After addition, r2 should become 10. Okay. Let us look into that. Now after execution of this statement, the r2 becomes 10. Now it's going to, the next instruction to be executed is subtraction. Subtract r1 from 1. Now actually r1 is a now. After execution of this instruction, r1 becomes 9. Okay. And again, since r1 is 9, the program flow go back to a loop. Again those addition instruction will be executed, and that addition result will be updated to r2. Now r1 will be decremented. Likewise, okay, this program instructions will be repeated for 10 times, okay, till r1 becomes 0. After r1 becomes 0, the program branch on node not equal, this actually becomes a false statement. That's why the loop will not execute further. And you can look out the addition result here. The addition result hexadecimal 37, that is stored in r2. The first 10 digits addition of first 10 digits in hexadecimal leads to 37, that's stored in register called r2. Okay. After execution of the branch termination, the program flow go back to a main program where it is in no operation state. Okay. So this is about how to debug the program. Okay. Now, so in this video we learned how to use Keel Microvision tools, and the same procedure has to be followed even in to execute the software program. Thank you.